Hello, Dr. Yampolsky. My name is Christopher Fattore. Today I'm going to be showing you an overview of my hybrid algorithm for finding the maximum click of a graph. First going to go over some information about graphs and clicks. Then I'll go over my approach I use for finding the maximum click of a graph. Then I'll outline my experiments. And then I'll talk about my results from those experiments. So first I'm going to talk about some information about graphs. So a graph is an abstract data structure. It contains vertices and edges. So you can see my graph here at the right where the vertices are the numbered circles and then the edges are the straight lines that connect the vertices. Vertices can also be called nodes. I'll use nodes a lot interchangeably with vertices throughout the presentation. So a graph is used to represent objects that are related in some way. So for instance, a street map. So say we have a street map of Manhattan where the edges represent the roads and the vertices are the intersections of the roads. So because graphs are used to relate objects together, streets intersect, and any street that intersects with one another is related because you can use one road to get to another road by passing through an intersection. Another good example, a graph can be used to represent a group of people where the nodes are the people and the edges represent a friendship or acquaintance. So if we pretend that this graph to the right here, each of the nodes is a person. So person 1 is friends with person 5 and person 2. Very easy to represent this with a graph. With the information about the graph, let's talk about what a clique of a graph is. So given a graph G made up of a set of n nodes and edges E, a clique is a subset of the graph G where all the nodes in the subset have an edge to one another. For example, 6 and 4 is considered a clique. 4 and 3 is also a clique. A slightly bigger clique would be 1, 5, and 2. Okay? All of the nodes have an edge to every other node in the graph. A maximal clique, okay, contains all of the nodes possible. Okay, what does that mean exactly? So for instance, 6 and 4 is a maximal clique. Okay, you can't add any other node in the graph to make the clique bigger because one of the nodes may not have an edge to that newly added node. Okay, for instance, a maximal clique would be 6 and 4. Okay, 3 and 4. Maximal clique would also be 1, 5, and 2. A clique that would not be a maximal would be, example, just 1 and 2. Okay, it's not maximal because you can add 5 to make it an even bigger clique. Hence, possibly the maximum clique, which is the biggest of all the maximal cliques in the graph. Okay, so 1, 5, and 2 is the maximum clique of this graph here. So an example, a real-life example of a clique. And a lot of times, you know, a group of friends can be considered a clique because they're all friends with one another. Okay, so a clique is a group of people where everyone in that group is a friend to every other person in that group. Very simple, very easy. So what makes the maximum clique problem so interesting? For one, it's NP-complete. NP-complete is a computational complexity where as the number of nodes or number of edges of the graph increases, so does the time to find the maximum clique. NP-complete solutions usually, well, they run in exponential time. So as you add more and more to the input, for example, the maximum clique problem, the input is the nodes and the edges of the graph, the longer it will take to find the maximum clique. It will grow exponentially. So because of this, we can't use brute force search, and we need to use another type of algorithm approach. So I decided to use a hybrid algorithm. I combined two algorithms to find the maximum clique of the graph. The first algorithm is the genetic algorithm, which is based off of the theory of evolution and natural selection. Evolution is the idea that species evolved from a common ancestor and explains how living things change over time and why they are the way they are today. Natural selection is an important concept when talking about evolution. Natural selection is a process where organisms with favorable traits are more likely to reproduce. In doing so, they pass on these traits to the next generation, and over time this process allows organisms to adapt to their environment. So for my genetic algorithm, think of it as that I'm generating new states from parent states, much like in nature where two parents create a child, very simply. The second part of the algorithm is the wisdom of the crowds algorithm. Wisdom of the crowds is a social phenomenon where the wisdom of the crowd is better than one expert. So this generates a state by using the collective opinion of all the other states. So for example, the first place that this was observed was at a county fair where a crowd was used to try and guess the weight of a cow, I believe. And one expert opinion was taken, and his guess was a lot farther away than the collective opinion of the entire crowd. So this has many applications in many other fields, so we're going to use it here as well. My approach. So to find the maximum clique of an inputted graph, I start with a randomly generated graph. Okay. Then, with this graph, with the nodes and the edges from the graph, I generate random subgraphs. This represents the initial population. Once I have the initial population, I can start the genetic algorithm. The genetic algorithm combines subgraphs together to form new graphs. I take some of the nodes from one subgraph and combine them with some nodes from the other subgraph. Two parent subgraphs are being combined to create a child subgraph. Once the subgraph is formed from the two parents, I calculate the maximum clique of each subgraph using the Braun-Kerbosch algorithm. This will give me the maximum clique of the graph, and from that I can find the clique number of the graph. I continually create graphs for a certain number of generations. In my test, I will show that I did 11 generations for the genetic algorithm. The next step is to use the wisdom of the crowds algorithm. The wisdom of the crowds algorithm finds the most commonly used nodes from the population. I iterate through all of the subgraphs and keep track how often each node was used in a subgraph. I ordered the list, and then I create a subgraph using the nodes that were most used in any subgraph returned by the genetic algorithm. Once I have this nodes to create the subgraph, I find the maximum clique size and the clique number, same thing, of the new subgraph. So, some of the experiments I performed. The goal was to compare the algorithm's performance on different graph sizes. So I wanted to see what the biggest clique found by the genetic algorithm was, and what the biggest clique was found by the wisdom of the crowds algorithm. I also recorded the running time of the program for each run, because I suspect that for bigger graphs, more denser graphs, the running time will be slower. So I did 10 runs on each data set, and I compared the genetic algorithm maximum clique with the wisdom of the crowds algorithm's maximum clique that was found. And then I compared this to the biggest possible clique if known. So I was not able to calculate the maximum click size for some of the data sets because it was too big. For the smaller ones, I was able to use a brute force approach and find how big the maximum click size of the smaller graphs were. But for the bigger ones, I was not able to do so. So let me talk about the results some more now. So overall, I found that it was able to find the optimal or close to maximum click size. Optimal meaning it's the biggest possible click for that graph for the data set. So overall, I found that for graph sizes 15, 50, 75, and 100, the genetic algorithm and the wisdom of the crowd algorithm, the biggest click size found by each approach was the maximum click size for the graph. For the data sets 250, 500, and 1000, I wasn't quite sure what the biggest click size was for those graphs, but I would expect from the smaller graph sizes that it would not be too far off. So for 250, the genetic best was only 13, but the wisdom of the crowd's algorithm improved upon that, being 14. For 500, I believe 16 is the known optimal. It was able to find 15 and 15. And then for 1000, the biggest click that was found was 17 and 17. So I use many different data sets for the experiments. I think I used about 7 data sets in all. Each one has a number of nodes with the number of edges. So the first data set I used was a 15-node, 66-edge graph. Again, the best found by the genetic algorithm was 8, the wisdom of the crowd algorithm was 8, and the known maximum is 8. So again, the goal of my experiments was to see the performance of the genetic algorithm and the wisdom of the crowd's algorithm on different size graphs. So the first data set was a 15-node graph. As you can see, the graph on the left here shows that over time, the population became more and more fit. What does that mean? Well, it means that the subgraphs in the population had bigger and bigger maximum click sizes, and the click number was higher for the subgraphs. So I distributed this between what is the maximum click size of a subgraph, of just one simple subgraph, what is the average of all the subgraphs in the population, and then what is the smallest subgraph in the population. So as you can see, the genetic algorithm did exactly what it was supposed to do. It was supposed to improve the population over time. As you can see, the average started off under 2, and then it improved to the average being over 5. And by generation 4, it was able to find the maximum click size of the graph. So we had good results with the 15-node data set. And as I'm going through the different data sets, you'll be able to see an illustration of what the graph looks like. Okay, so the graph will show each point that is a part of the click, and then an edge will be drawn to every other node in the graph that's a part of the click. These nodes here, just the circles without any filling, are not a part of the click. The next data set was a 50-node, 694-edge graph. Okay, again, we wanted to see the genetic algorithm improve over time, improve the fitness, improve the maximum click size of each subgraph in the population as each generation runs. So again, you'll see that for each data set, the average will increase over each generation, the maximum will increase, and if it finds the biggest maximum click size, it will plateau, and then the minimum should also increase over time. Same with the 75-node graph, which had 1,626 edges. The average increased, the minimum increased, and the maximum increased. So I won't go into too much detail, but again, the 100 node graph saw similar results. It had 2,892 edges. So again, as more nodes are added, more edges are also added with the data sets. And the algorithm's still performing very well. Although, as I'll show after this, the running times begin to be slower. I had similar results, again, for the 250 node graph, which had 18,563 edges. But this one is starting to be a little different. So we see that the genetic algorithm only returned a subgraph with a maximum click of size 13. The wisdom of the crowd's algorithm improved upon that with the size 14. But the maximum is still in question, so I wasn't sure exactly what the maximum click size of the 250 node graph was. But we can see that the maximum click size, the biggest maximum click size of a subgraph, plateaued at around 6, with the overall average still increasing, the minimum still increasing. So this would lead me to think that, you know, maybe 13, possibly, well, because wisdom of the crowds was 14, maybe the maximum is 14. But so again, the 500 node graph with 74,206 edges. Again, I was not able to find the maximum, but the genetic algorithm and the wisdom of the crowds algorithm was only one node off. And you can see in the illustration that it is a very dense graph. And you can see the genetic algorithm improves the population over time. The overall population is becoming more fit throughout each generation. The last data set was 1,000 nodes, which was about 307,085 edges. Again, the genetic algorithm returned 17. Wisdom of the crowd algorithm returned a maximum click of a subgraph of size 17, and the maximum is unknown. But you can see that the population, the overall fitness of the population increased over the running of the genetic algorithm. So the overall results. The overall results table here shows the biggest maximum click size of a subgraph returned by the genetic algorithm and the wisdom of the crowd algorithm. I did this test because I wanted to see how often the wisdom of the crowd algorithm improved upon the answer returned by the genetic algorithm. So you can see some cells of this table are highlighted in blue. Those are cases where the wisdom of the crowd algorithm was able to improve upon the biggest maximum click size of a subgraph returned by the genetic algorithm. So, for instance, a big improvement for run 6 of the random 75 node graph, the genetic algorithm only returned a subgraph with the maximum click size of 10, but the wisdom of the crowd algorithm was able to return a subgraph with a maximum click size of 13. So I saw about similar results for each data set. So the wisdom of the crowd algorithm, although it did not always improve upon the answer returned by the genetic algorithm, it did for about, I believe it was 17% of the cases, or approximately 2 times for out of 10 runs for the bigger data sets. So again, overall, the results were good. Sorry about that. So again, I also wanted to keep track of the running times of the program when it was looking for the clicks and the click sizes. So I found for the, we'll go off of average, that the smaller data sets, you know, of size 75, 50, and 15 all ran under a second. Size of 100 was about 2.3 seconds. The graph of size 250 was 7 seconds. The 500 node graph was only, you know, a bit bigger, a bit longer. Was about 23 seconds on average. And then the 1,000 node graph was very large. It had over 300,000 edges, and it averaged about 2 minutes per run. But the algorithm performed well overall. So, in conclusion, the results showed that the genetic algorithm improved the overall fitness of the population over each generation for the subgraphs in the population. The collective average, the maximum, and the minimum all increased after every generation. The wisdom of the Krauss algorithm improved upon the biggest maximum click size for a subgraph returned by the genetic algorithm, which is another thing that I wanted to show in my experiments. So overall, the hybrid algorithm performed well on a variety of graph sizes. The running time increased as graph sizes got bigger, but it's still a very good approach for solving the maximum click problem. And thank you very much.